So welcome everyone, and welcome to Leonardo, of course, and thank you very much for accepting our invitation. And today we're very happy to have Leonardo Rastelli as a speaker for our colloquium. And just a couple of words, I mean, you know him, but so Leonardo got his PhD at MIT, and then from there he moved to Princeton, where he was faculty member. And from Princeton, he moved to Stony Brook at the Young Institute by now more than 15 years ago. And now he's there as a Renaissance chair in physics. So especially in the last years, of course, he's been one of the most prominent researchers in the study of Bootstrap. And this is witnessed by the fact that now he's the director of the Simons collaboration on non-perturbative Bootstrap. And well, judging by the title, I think today we're going to hear about what to do with Bootstrap in quantum gravity. Thank you.
Thank you very much for the kind introduction. It's a great pleasure to give this virtual talk in Florence. I love Florence. That's where I was born. And again, so grateful for the opportunity to present this colloquium. I was told that this is mostly theorists audience, but nevertheless, my colloquium will be rather general. It will get perhaps a little bit more technical towards the end, but I try to keep it to emphasize conceptual aspects more than detailed calculations. And it goes without saying, you should interrupt me at any time. If it's too slow, tell me that it's too slow. If you have any questions, please ask. So as Domenico was mentioning, I will today tell you how to apply the Bootstrap paradigm to quantum gravity, to carve out this very lofty goal of carving out the space of consistent quantum gravity theories and perhaps ultimately nailing the theory that corresponds to the real world. The program is still a little bit in its infancy, but we're making progress. And I will also try to frame it in the context of the more general Bootstrap program and see what, in the context of what the community has achieved in the past several years. So, okay, so let's try. So what is Bootstrap? It's a funny phrase, as often is the case with names that people then voluntarily adopt. It started as a derogatory term, and of course the metaphor is well known. You're trying to lift yourself up by pulling your own bootstraps, which is obviously impossible. And so the phrase started in the late 19th century in the American press as a way of mocking someone who was trying to do something that made no sense. But then it quickly changed the meaning to the idea that you're trying to, just use your own resources. It also has a political meaning. You should not give money to the poor because they should be able to lift themselves up by their own bootstraps. And of course, in science, or for example, even in computer science, it has come to mean that it's some sort of a self-starting process. So it's a process that doesn't really use any external input and proceeds essentially by internal consistency requirements. In theoretical physics, the bootstrap phrase was started to be used, I think, in the late 50s and 60s. In a related but different sense, which was the idea of trying to constrain and ideally solve a theory just using symmetry and consistency requirements. So the first incarnation of the Bootstrap program in theoretical physics was in the context of the theory of the strong interactions. People were despairing. They were finding a new hadronic resonance almost every week, and they were despairing of putting order into this chaos, and thought, well, perhaps it's truly impossible to write down a microscopic Hamiltonian or Lagrangian model. Let's just try to see what are the possible very general constraints on the hadronic S matrix and see whether that could possibly lead to a solution of the theory. And in more modern times, we can actually be rather precise by what we mean by the Bootstrap program in theoretical physics. The emphasis has changed a little from trying to find a specific theory. For example, in the 60s, people were trying to actually find the theory of the strong interactions. Now the meaning is a little different. There's this modern idea of theory space. The idea started with Ken Wilson, but it now has an even much more general meaning. And I will make it precise in several examples later. The space of putative possible theories, parameterized by an infinite set of parameters, perhaps, and try to carve it out, try to see out of these imagined possible words, which one are truly consistent and compatible with the rules of quantum mechanics and with the symmetries that you may want to impose. So that's the modern meaning of the bootstrap. And of course, all of this is rather philosophical, rather vague, but it can be made surprisingly precise, surprisingly effective once I start making more concrete what I mean by a theory. So I need to tell you a set of axioms that define a theory, and then the bootstrap program will be actually find all possible instances that incarnate those axioms. And the most successful incarnation of the bootstrap program is in the context of conformal field theory. Conformal field theories are rather special quantum field theories, which are invariant under transformations that preserve angles. And there are really two versions of this. We could consider theories purely defined in space, that is the physical context, say, of statistical mechanics or condensed matter systems, where we're looking, for example, equilibrium properties of a sample of material, and so we don't care about time. Or, as the case may be, we're considering the theories defined in space-time. That's, of course, the physical context of particle physics. And here in this, I'm illustrating here a conformal transformation. Locally looks like a dilation and a rotation, and it sends this square grid into this distorted grid. Now, of course, conformal transformations include a overall dilation of space, and so they appear to be extremely special invariances that normally, of course, we do not have in physics, because we have intrinsic length scale, intrinsic mass scales. And so it might seem from this perspective that conformal field theories are really very special and very rare, but in fact, sort of the opposite is true. Conformal field theories are central to modern theoretical physics. And one idea why they are central is because they are lampposts. They are special points in this space of theories I was alluding to before. And one way in which you get to conformal field theory is by considering extreme kinematic limits. For example, if you look at particles scattering at very high energy, you can neglect mass scales and length scales, so the theory will look conformal. And conversely, also, if you look at extremely large distances, extremely low energies, again, it's the case that you can neglect the intrinsic mass scales of the system. And so on very general ground, it's actually believed that the most general definition of a quantum field theory is a theory that interpolates between a conformal field theory at very high energy and a conformal field theory at very low energies. The second picture in my slide here illustrates a very canonical use of conformal field theory using the theory of second order phase transitions. Here, the phase transition, the correlation length becomes infinitely large. And so again, you have this phenomenon that you're able to neglect intrinsic length scales because they're negligible with respect to the correlation length, and the system loses memory of the microscopic degrees of freedom and enriches some sort of universal description at large distance, which is controlled by conformal field theory. This particular picture illustrates the phase transition to liquid to superfluid helium, about which I will have to say a little bit more in a minute. And the third picture illustrates another canonical use of conformal field theory, which describe quantum critical points of the kind that are relevant, for example, or are believed to be relevant for the theory of high temperature superconductivity. And so both practically, because they apply to many interesting physical phenomena, and conceptually, because there's this idea that you can define a general quantum field theory as an interpolation between a conformal field theory, high energy one and low energies. Conformal field theories are truly central. And because of this enhanced symmetry, the setup is particularly clean. One can formulate a set of mathematical axioms that a conformal field theory should obey. And so in this particular context, then the Bootstrap program becomes very concrete, and it's really the very ambitious goal of compile a complete catalog of all consistent conformal field theories in various dimensions. So the idea is an old one. From the early 70s, Ferrara, Gatto, Grillo, and Polyakov formulated the axioms, and then there was this famous, beautiful work by Belavin, Polyakov, Samologikov, and Zavolodchikov that used the fact that in two-dimensional conformal symmetry is infinite dimensional because every holomorphic transformation of coordinates is conformal, and that led to the solution, exact solution of many beautiful models, including the two-dimensional critical Ising model. And the modern era in this business started with a very nice paper in 2008 by Rattazzi, Richkov, Tony, and Vicky, who used this more modern viewpoint. Rather than trying to solve individual theories, we have this idea that we have this space of putative theories, parameterized, for example, by the critical exponents of the conformal field theory and other quantities. And the idea is that we want to carve out theory space rather than identifying necessarily the exact solutions. And this carving out is in some sense a tactical retreat because you're asking less. But in some happy cases, it turns out that the carving out is so powerful that you restrict yourself to a tiny little island, which for all intents and purposes amount to an exact solution of the theory. And okay, so that's the paradigm, and we'll illustrate it now in an example. But to reiterate, so the slogan that I will use over and over in this colloquium is not anything goes. And this is the first incarnation, not anything goes in conformal field theories. And the idea of this carving out is illustrated here by a picture that I stole from Slava Richkov. You have your guess for what the theory should look like. For example, you have a hunch that liquid helium should have certain critical exponents, and you feed your guess to the Bootstrap oracle. The Bootstrap oracle is like one of these ancient oracles in Greece. You give that to the god, and the god never says yes. The oracles in Greece used to be famously very ambiguous, but it can't say no. The oracle either says no, and if it says no, it means that your guess is ruled out. You go back to the blackboard, or it might say, well, I cannot really exclude it, so it's a maybe. And by implementing this oracle numerically, you get to carve out theory space, of which I now want to give you a rather recent example regarding the phase transition between liquid and superfluid helium. So there's this famous, very dramatic divergence in the specific heat of liquid helium around 2 Kelvin. It's called the lambda point because of the characteristic shape of the specific heat around the phase transition. And the divergence happens with a certain power of alpha that controls the divergence of the specific heat near the critical temperature. And alpha is in turn related to a quantity that those of you who know the language of conformal field theory will recognize as more canonical, which is a certain conformal dimension, delta S of some scalar operator. And this phase transition is famous as corresponding to the best measured critical exponent in all of physics. The experiment is actually very hard to do on Earth because of the pressure gradient in the sample. It turns out that only a very tiny layer is a criticality, and layers above or below are either above or below criticality. And so if you actually want to achieve any sort of control, experimental control on critical exponent, you have to do the experiment in space. And the experiment was actually done on the space station in the 90s. It's probably the only good thing ever to come out of the space program. And there is a very dramatic discrepancy, an 8 sigma discrepancy between the experimental determined valued in space and Monte Carlo results. And so here is actually a practical application of this carving out of theory space methods that the modern Bootstrap program can achieve. So here I'm representing a three-dimensional slice of the infinite set of parameters that characterize the phase transition. Those are the critical exponents or conformal dimensions of local operators, if you know the language of conformal field theory. It doesn't really matter what these numbers are, but this picture illustrates the idea of carving out. So a priori, you could imagine that there is a theory that corresponds to each point on this in this parameter space. In fact, the parameter is really infinite dimensional. Just look here, this particular three-dimensional slice. But in practice, this is not so. So in this picture, we see, first of all, the gray or brown parallel planes here are experimental window. And the green region is the Monte Carlo result. You see, they miss each other very dramatically. This 8 sigma discrepancy. And this much smaller blue region is the carving out achieved by the bootstrap. So you see, it's compatible with Monte Carlo. It's much more precise. And the blue region, I'm not giving you any of the math. I will illustrate the general philosophy in a somewhat different context in a minute. But the idea is that the blue region is obtained only by inputting extremely general principles. The fact that probability are positive, the fact that the symmetry has the system has conformal symmetry, and it has the symmetries that should correspond to this particular phase transition. So basically, from pure thought and a lot of ingenuity, putting this on a computer, you find this rigorous exclusion region, which you see fundamentally amounts to a theoretical determination of the critical exponent, because the region is so small that the errors are actually much smaller than Monte Carlo. And so this actually resolves the discrepancy in favor of theory. So Monte Carlo was right and the experiment was wrong, either because they made a mistake or because they were too optimistic about the errors. We're not going to find out anytime soon, because no analogous experiment is planned in space at the moment. Anyway, again, you should interrupt me, ask for questions. If this is too elementary, I can make it harder in absolutely no time. I'm unsure about what is the level expected for this theory colloquium, but please tell me. Should I proceed?
I think it's perfect like this, honestly.
Okay, so thank you. So I'm now switch gears a bit. So you will see this. I'm going to tell you a whole complicated tale that will have several different parts that at first sight may appear a little disconnected from each other, but I promise there is actually logic to it all. So I'm now switching gears and tell you about a related but somewhat different incarnation of the bootstrap, which is known as the modular bootstrap. And the reason I'm doing it, first of all, there will be a very concrete physical application in a few minutes to quantum gravity, but also because it's sort of the simplest setup in which I can actually write some equations and tell you how the bootstrap program works in general. And so to write the equation that corresponds to the previous story, determine the critical exponents would be a little harder. Here, the story is a little simplified, but the general philosophy is identical. So the modular bootstrap is specific to 2 dimensions. So 2 dimension means either 2-dimensional space if we're doing statistical mechanics, or 1 of space and 1 of time if we're doing Lorentzian physics. And we're interested in considering 2-dimensional conformal field theory at finite temperature. So famously, a theory of finite temperature is described by a Python integral where we take the theory in Euclidean time and make Euclidean time periodic. So in this particular context, we want to also make space periodic. So we take a theory defined on a spatial circle. For example, you could say that this purple circle is space. And then we also make Euclidean time periodic. So all in all, the theory is defined on a torus, where periodicity in Euclidean time corresponds to inverse temperature. The famous dictionary that relates theory at finite temperature to a Euclidean path integral of this kind. By the way, there's really no loss of generality in taking the theory on a special circle, because if the theory is on a special circle, it means that the full theory is defined on a cylinder where the vertical direction is time. But it turns out that in 2 dimensions, you can map the cylinder to the plane by conformal transformation. So really any 2-dimensional conformal field theory can be placed on a cylinder with no loss of generality. And so any 2-dimensional conformal theory of finite temperature will be described by studying the theory on this torus. And so the partition function will then have of this Euclidean theory, we'll have a statistical interpretation will be the usual sum over the states of the theory of the Boltzmann factor, e to the minus beta ei. So the sum here is over all states, which means that if there are degeneracies, if there are 2 identical states or several identical states, they're counting as separate indices in this sum. And now comes the there are really 2 important constraints here. The first constraint here is the fact that this sum is a positive sum. You see, it's Boltzmann factors each weighted by 1 or by an integer if I were to account for the degeneracies. I will not really use the fact that these are integers, but I will definitely use the fact that these are positive quantities. You know, it's a sum over with positive weight. So that's a positivity constraint. The other constraint, which generally we could call it crossing constraint, is the fact that once I formulate the theory on the torus, who's gonna tell me which is space and which is time? I can just steal my head and change my mind about what is space and what is time. And given that the theory is scale invariant, the only thing that can matter is the ratio between 2 circles. So that means that I have this surprisingly, but simple equality that says that the theory at temperature beta really has to be the same as the theory at temperature 1 of beta. And there is clearly a certain amount of tension between these 2 conditions. And the tension is such that if you give me your favorite set of energy eigenvalues, it will simply fail to obey this condition. And so that illustrates the idea that not anything goes. These are bootstrap equations. In fact, it's an infinitely many equations. For what we are trying to determine here is the spectrum of energies. Those are the infinite set of data analogous to the critical exponents in the previous slides. And this infinite set of data that specify a putative theory are not arbitrary, because they must satisfy this infinite set of equations. Why is it infinite? Because this equation must be satisfied for each value of beta. And so the way to milk this bootstrap cow is to, first of all, trivially rewrite this equality in this fashion, where again, what's important here is that each of these factors is weighted with a positive coefficient. And then try to distill the information which is contained in this infinite set of equations in some sort of a clever way. If you proceed blind, you don't go very far. But the idea is,
I have a question.
Yes.
Why is this equation a set of infinite set of equations? This seems to be a single equation, z beta equals z one
Because
one
beta, sure, it's an equation for each value of beta, but beta is an arbitrary real number.
Okay.
So what we're trying to determine here is the eigenvalues ei's, right? So for each value of beta, we get a constraint on the ei. So it's really infinitely many constraints. But rather than trying to constrain the theory by specifying blindly different values of beta, there's a better way to do it, which is to construct a linear functional of this kind. So we take derivative with respect to beta at the crossing point, and we weight them with some cleverly chosen weight alphas in such a way that we can extract the information contained in this crossing equation more efficiently. So it's not so clear what kind of function you should be choosing, but what kind of function you should be choosing depends on the question you're going to be asking. And so the whole art now of the bootstrap is to construct clever functionals that answers the questions that you may have about the spectrum ei. So by the way, I should give credit to Simeon Hellerman, who came up with this incarnation of the bootstrap and the follow-ups. And
I have
we will come
another
back
question.
to this story in a minute. Yeah.
So,
Sorry, there was a question.
yeah, so for a specific CFT, for a specific conformal field theory, the spectrum is fixed, right?
Correct.
So if the spectrum is fixed, then this particular equation, Z beta equals to Z of 1 by beta would be satisfied for a single beta, not for many betas. Isn't
No,
that correct?
definitely for all betas. That's the whole point.
How
The
can it be
spectrum, the EIs are fixed, but beta is just the temperature.
Yeah.
Right.
But if the equations are satisfied for a specific set of EIs, then I don't see how they can be satisfied for a different set of betas.
I'm not really
specific
parsing
set
what
of
you're trying to say. The whole beauty of this is that it's precisely a strong constraint. For a conformal field theory to be consistent, you have to be able to choose a set of EIs, which of course I agree are fixed for any given CFT, such that for any choice of beta, this equation is true. And you could say, how could that possibly be? Well, that's your lack of imagination. I mean, we know, of course, of many examples where this is true. We can just check that this equation is obeyed. This is the S transformation. The reason this is called the modular bootstrap, I didn't want to get into this nomenclature, but this is the S modular transformation. It's a very non-trivial thing. The generic spectrum will not be modular invariant. And so this is precisely a constraint, or it's the S part of the constraint of the modular transformation. It's absolutely non-trivial. And it is infinitely many equations, one for each beta. Okay, so again, I'm meandering around in this conceptual space, and now I'm going to switch gear again, and then eventually all this will come together. And so I illustrated the power of the bootstrap, first of all, in constraining critical exponents, and then in constraining two-dimensional CFTs using the modular property. The critical exponent story had really to do with the crossing symmetry of 4-point function, but I didn't want to get into those technicalities. And so I illustrated the bootstrap in the context of modular invariance, which will prove useful in a minute, I promise. But then, of course, we can keep going and get even more ambitions and ask, what about, the most fundamental question in physics? What is the possible, what are possible consistent theory of quantum gravities? And the approach that we take here is a very pragmatic one. We're not going to build a Planck scale accelerator anytime soon. But of course, we know that at low energies, we have massless gravitons, we have Einstein gravity. Einstein gravity should be really understood, I think, by any sane person as an effective field theory. Certainly, there's no sacred principle that we should just have square root GR. We should understand. We should think of Einstein gravity as just a low energy approximation to a theory that contains higher derivative correction. Then, of course, we can have matter fields illustrated here by some scalar and its higher derivatives. And so, given a low energy effective field theory that contains gravity, by which I mean you tell me the particle content and its interactions and its set of at least the first few higher derivative corrections, you can ask the very good question: is this some random garbage that I can write down, or is it something that comes from a truly consistent UV complete theory of quantum gravity? And in this context of constraining quantum gravity theories, this program has a funny name. It's called the swampland program. And the metaphor here is that we're trying to distinguish the swampland of garbage effective field theories that really cannot be obtained as low energy approximation to a truly consistent theory from the dry terrain of the good theories that really come from fully consistent theories. And the metaphor is particularly apt in the context of the bootstrap, because actually the first incarnation of the bootstrap metaphor came from the adventures of the Baron de Munchausen, who didn't quite try to pull himself out by his own bootstrap, but he actually wanted to emerge from the swamp by pulling his ponytail. And so that's the question we are going to ask. can we use this very general idea of constraining, carving out theory space in the context of quantum gravity? And okay, now those of you who are who are certainly the more theoretically inclined people in the audience will say, okay, but of course there is at least one corner of theories where we surely can do this, and it's theories of quantum gravity that live in asymptotically anti de Sitter space. So okay, this is not the space for me in this colloquium to review the whole holographic correspondence, but surely all of you are either experts on it or have heard many talks about it. There is this beautiful mathematical correspondence that asserts that if we consider a theory of quantum gravity in this very symmetric box, which is anti de Sitter space, which is space of constant negative curvature, asymptotically that is, that is entirely equivalent to conformal field theory that lives on the boundary. So here the cylinder sketches anti de Sitter space. The bulk of the cylinder is anti de Sitter space, and the surface of the cylinder is the boundary of the space, and that's where the conformal field theory, quote unquote, lives. So in this particular case, it would be three-dimensional anti de Sitter space with a two-dimensional boundary CFT. And so here, what is illustrated here is the idea that we can perturb the surface by inserting some local operators, and the way we should think of this perturbation here by four little wiggles on the boundary is that corresponds to a scattering experiment in the bulk. And so we can think of, in some sense, the correct analog of the S matrix for anti de Sitter space are correlation functions of local probes on the surface of the cylinder, which is a two-dimensional conformal field theory. So that is the sense in which conformal field theories are holograms, because living one dimension less for theories of quantum gravity anti de Sitter space. And then at this point, then at least one part of the program of bootstrapping quantum gravity becomes clear, where surely for theories that live in anti de Sitter space, we can just literally map the problem of bootstrapping quantum gravity to the problem of bootstrapping conformal field theories with some certain caveats, because as I will illustrate a little bit more concretely in a few slides, what do we really mean by quantum gravity theory in the bulk? Well, in order for the theory to be recognizable as the theory of quantum gravity, it better be that it has a weak coupling limit. Otherwise we could just take this as a definition of what is quantum gravity in the bulk. But if we want this to be a little bit more than a definition, we should also have some independent expectation from what the theory does in the bulk. And in the case of gravity, we only can have that expectation if we can use semi-classical methods. In other terms, if the Newton constant is small. And that translates into the condition that the theory on the boundary should have a very large number of degrees of freedom. So to be more precise, then the problem of bootstrapping quantum gravity in the Sitter space, or at least semi-classical quantum gravity in the Sitter space, something we can understand concretely as a correction to Einstein gravity plus small corrections, really becomes the question of understanding a special corner of conformal field theory. Here you have a large number of degrees of freedom and some other technical conditions. And just again, to say something very general, and I promise something with more questions will come in a few slides. The original hint for holography came from Bekenstein and Hawking, and it's this idea that black holes in classical general relativity, they are, essentially unique solutions characterized by the mass and the angular momentum, but they are not really black. They radiate. They very much behave like thermal objects with a gigantic entropy. And the entropy is the area in Planck units. And so that's the first hint of holography, in the sense that the number of degrees of freedom of black hole scales with the area, not with the volume. And it's also this, by now, very serious idea that I think now has pretty much been established in several toy models, generally believed to be true, that we should really understand the black hole as a thermal with the gigantic number of microstates. And so, for example, I did a calculation here for the supermassive black hole at the center of the M87 galaxy, which supposedly has this image. The image, of course, is a bit of a fake, but whatever. So if you do the calculation here, just because the black hole is astronomical size and the Planck length is so small, you get this gigantic entropy. And so two ideas here are important. First of all, if we use semi-classical gravity, which in the Planck length is very small compared to standard lengths of our universe, so say astronomical distances, the entropy is gigantic. And the second idea is that the entropy scales like the air. And so that finally, we are now finally zooming in on a first concrete application of this general set of ideas, which is try to bootstrap, in the modern sense, and to find the space of possible theories of gravity in three-dimensional de Sitter space, which by the holographic correspondence will be mapped to the problem of finding special sets of two-dimensional conformal field theories. And of course, this is a bit of a toy model, because what we really would like to do is in 4 dimensions, and I will tell you towards the end of the talk what we can currently do in higher dimensions. But even in 3 dimensions, by which I mean 2 + 1 space-time dimensions, the question is very interesting, and it's a notorious question in theoretical physics that is still very much unsolved. And the reason that the problem, of course, is simpler in 2 + 1 dimension is that there are no gravitational waves. There are no truly propagating gravitons. However, remember that we are studying the theory in anti-de Sitter space, which is a bit of a box. And a more careful analysis actually shows that although there are no truly bulk gravitons, there are something which you may call boundary gravitons. There are sort of ripples of the surface of the box. Those of you who know these things, those correspond to the Virasoro modes of the 2-dimensional conformal field theory. And then a very sharp question that we can now ask is, what is the simplest theory of 3-dimensional gravity? Could it be pure gravity? And I need to specify what I mean by that. So here I'm writing out the Einstein-Hilbert action with a negative cosmological constant, plus dots and a question mark. Could I just have Einstein-Hilbert and nothing else? And what would that even mean? Or do I need to additional degrees of freedom, string, supersymmetry, or whatnot to make the theory consistent? And we can now make the question extremely precise using the language I've developed. First of all, we need to have boundary gravitons. Those are implied by this Einstein-Hilbert action term. And moreover, it's easy to see, and one can prove this by Bootstrap methods, but even just by intuitive reasoning, that boundary gravitons are clearly not going to be enough, because this semi-classical action emits black hole solutions. And if the Newton constant is small compared to the ADS scale, which it needs to be in order for this action to have any meaning, then those black holes will have a gigantic entropy. And that entropy needs to be explained by some additional very massive microstates. So the minimalistic guess for what is the simplest theory of quantum gravity in 2 + 1 dimension is just boundary gravitons and whatever makes up the black hole microstates. And perhaps nothing else. That's the minimal thing you could possibly have. And we can now put some additional estimates here. The black hole entropy, as I just told you, scales like the area, which in 3 dimensions is just the length, over L Planck, which in 3 dimension L Planck scales like a Newton constant. And so this is gigantic if the Newton constant is small, which it should be if you want to think of this as some sort of standard semi-classical theory of gravity. And this particular ratio, L over G, is also the central charge of the 2-dimensional dual conformal field theory, which is, again, many of you are experts, but the central charge is a measure, actually in 2 dimensions, a very rigorous measure of the number of degrees of freedom of the dual conformal field theory. So this illustrates the slogan I was mentioning earlier, that if we're interested in semi-classical gravity, we should take the central charge to be very large, or the number of degrees of freedom of the dual theory to be very large. And and so now we have one of the first correspondences that I was already saying words. The conformal field theory on the torus, the two-dimensional conformal theory of the torus, really gives us the bulk action in anti-de Sitter space. So we can now really formulate the question as a question for the modular bootstrap. Okay, so finally the modular bootstrap that was introduced earlier just as an illustration of the bootstrap axioms now has a physical application to answering at least one version of this question of consistent quantum gravity theories. And the idea is, so we want to specify the theory, the quantum gravity theory in the bulk. It's a quantum mechanical theory, so that there will be empty space that corresponds to the vacuum. We will have energy E0 that we could set to 0 by a shift. And then now we can give a very precise quantitative meaning to the question, what is the simplest theory? Well, the simplest theory is the one where the gap to the next state will be the highest, right? We know that the theory cannot just contain the vacuum and its ripples, because that would be inconsistent. We need microstates for the black hole. And now we can ask how high we can push the next excited state so that the theory is consistent. Okay, so that would be a very good quantitative way to make precise what we mean by the simplest theory of three-dimensional quantum gravity. And the very nice insight is that if we specify the central charge, then we actually, the modular bootstrap gives us an upper bound on how far we can push the first excited state. In other terms, it's not possible to have a completely empty theory that just contains a vacuum. That is what I was saying earlier. We must have at least a black hole microstates, but now we can make this, we can now make this quantitative without any appeal to this semi-classical intuition. If we do not find at least some states below a certain gap that depends on the central charge, then this famous set of equations I had earlier is not satisfied. And so the picture is, yes?
From the bulk point of view, you can have as massive black holes as you want, right? So
yes,
from the bulk point of view, you can have as high energy states as you want.
correct.
So what interpretation would that have here?
Yeah, but you see, we're asking the converse question. The question is not how, yes, of course you can have states at extremely high energy, but the question is, what is the lowest energy that must appear for the theory to be consistent? Okay, so that energy can, the point here is sort of the converse. We cannot push those states to be arbitrarily high. That we need to have states at energy that is not bigger than something. So there is an obstruction to making the theory completely empty, and that obstruction comes from the modular bootstrap.
No, but from the bulk point of view, there is no obstruction, right? From the bulk point of view, you can have as high energy as possible. So that should have an interpretation in the conformal.
But your logic is backward. Yes, you can have as high energy as possible, but there are also solutions with a minimal energy. So what do you do with those? You know, the BTZ black hole is there, and it's a legitimate solution. You cannot just throw it out. The question is not how high the energy can be, but how small it can be. Right?
No, here you are giving an upper bound. You are giving an upper bound on the energies.
So Nata, if you don't mind, could you keep this for the discussion session at the end of the talk so that we get till the end first?
Okay.
I'm giving an upper bound on the minimal energy, A1 about the vacuum. Okay, so we have an infinite set of energies, E0, E1, E2, E3, E4, and you're preoccupied with E1 million. I'm preoccupied with E1. I'm preoccupied with the first excited state. I'm telling you there's an upper bound on the energy of the first excited state.
Okay. Okay.
So you see, here is a sketch of the spectrum. There's the vacuum, and then, as I was promising, there are these little ripples of the boundary of the box, which for those of you who know this language, are the Virasoro excitations of the vacuum. And then we know, or we expect from this microscopic interpretation of the black hole entropy, that we should have microstates that correspond to the lightest BTZ black hole coming at energy of the order C/12. And the question is then, what is the modular bootstrap going to tell us about where the gap actually is? And so one can study this numerically. And there are two aspects of this numerical study. One is two very strange numerical surprises that happen for a very special value of the central charge, 4 and 12. And the second one is the asymptotic growth of the gap. So let me first discuss the numerical surprise at this special value of the central charge. Absolutely out of nowhere, one finds that the gap, for example, for C=12, but something similar will happen for C=4, is with extraordinary numerical precision equal to 2. And also its degeneracy is an integer, again, with extraordinary numerical precision. It's not just any random integer, but it's this famous number, 196,884, which is also the famous equation. It's equal to 196,883 plus 1, where this number here, the one before the plus 1, happens to be the smallest representation of the Mossad group, which is the largest sporadic group. And in fact, the whole partition function, this particular value of the central charge, converges with very good numerical approximation to essentially the J modular function. And something similar happened for C=4. Again, there's a simple modular function that explains the optimal theory. By the optimal theory, I mean the one where I've pushed the first energy eigenvalue about the vacuum as high as possible. So we have holomorphy, right? These are holomorphic partition function, but again, that was not imposed at any stage of the calculation. Holomorphic comes as a total surprise. We have modular functions. We have Mossad symmetry in a way that is completely mysterious. So that's surprise number one. And then the second thing, which is not a surprise, but just a detailed numerical calculation, is that one can extrapolate the asymptotics and find that the gap, the optimal gap that you can get by this method, is something like C/9. So actually, unfortunately, C/9 is, of course, bigger than C/12. So these numerical methods haven't quite been able to push the black hole threshold all the way to the natural expectation, which will be the microstate mass of the first BTC black hole. And well, I'll come back to this, but that would have been the natural guess, that the gap has to appear at the microstate of the black hole. And this method tells us, well, there has to be a gap, but we haven't quite been able to push all the way down to the natural threshold. Okay, so now I'm going to switch gears again, and then eventually in 10 minutes or so, all these ties will hopefully merge together. And I'm going to ask a completely totally different question, a question in pure math, having to do with the sphere packing problem, which is a famous ancient problem, which asks what is the densest configuration of identical sphere in the Euclidean dimensions. It's a deep mathematical question connected to all branches of math, modular forms, number theory, cryptography. And what's peculiar about it takes a very different form in each space dimensions. Has only been solved in this very small set of dimensions. In one dimension, of course, there's nothing to do. You know, a sphere is just an interval. You just put them one next to the other. In two dimensions, it's easy to convince oneself that the best way to stack coins is the obvious one. The proof is elementary, but little subtle. A complete proof is only credited to Toth in 1940. In three dimensions, again, it's a long-standing problem that was first formulated by Kepler. And of course, it's obvious that the way you stack oranges or cannonballs is the most optimal way. You take the obvious stacking on the plane, and then you stack such planes one over the other. if you think a little bit about it, one way to do it is in a regular way, by putting the bolts at the centers of the face center cubic lattice. But actually nobody stops you, given that regular configuration, to start sliding the planes independently one from another without changing the density. So there's actually infinitely many ways in which you can stack oranges or cannonballs that have the same average density. And what Kepler conjecture is that these ways are optimal in the sense that no denser packing can be found. In fact, the story is interesting. So this originated, as always, often is the case in this kind of mathematical or physical problem, by a very practical question. So, there was this Thomas Harriot was a friend of Kepler. He was a mathematician and astronomer, and he in turn was an assistant to Walter Raleigh. Eventually was killed he was an adventurer, an explorer, a warrior, probably not a very good man, but he was interested in making war and commerce with the New World. And so he asked Harriot the obvious question: can you count how many cannonballs I can put on a ship? And he gave, the answer is actually elementary, and then got Harriot thinking about, well, but is that actually the optimal way? Can we prove that that is the optimal way? And that's what Kepler, inspired by correspondence with Harriot, conjectured. You see here a picture from his paper on the 6-corner snowflake. You know, Kepler had all sorts of crazy ideas about how to prove that a snowflake has only 6 corners. He didn't succeed, but in the process, started his whole business. And the proof only came in 1998 by Hales. It's a very complicated proof that essentially you can eventually reduce yourself to a finite number of configuration that you can check by computer. And the proof is actually famous in Western mathematics because very recently, I think in 2014, is one of the first truly important proofs that has been formalized, in the sense that now there's a certificate given by a machine that runs a formal logic code that tells you the proof is actually fully rigorous. Every step of the proof has been checked by computer. Anyway, why am I telling all of this? Well, because it came as a gigantic surprise to the community when on Pi Day in 2016, Marina Wiazowska put on the archive an extremely short and elegant paper that proved that in A dimension, the EA lattice, when you put the spheres at the centers of the A lattice, is optimal. And the techniques were generalized instantly, basically a week later, with some collaborators to 24 dimension, where it was proved that the Leech lattice is also optimal. And how did the story go? Well, the story that Marina Wiazowska perfected really had a longer history. She built on a very nice paper by Conan Elkes in 2003. And what Conan Elkes had done is something that hopefully will now start ringing a bell. What Conan Elkes showed is that if you are able to construct a function, just a real function, f of r, with certain positivity properties, and that obeys a certain crossing property under Fourier transform, that function gives you an upper bound on the possible density of spheres. The upper bound here is shown by this red curve, and these blue dots with the jagged line connecting them are the best known packings in various dimensions. So one thing that you immediately notice is that the known packings are very regular. There's no claim that these are the best packings. These are the best known packings, especially as you go to higher dimension, it's conceivable that better packings could be found. And one feature that you immediately notice is that, well, one dimension is sort of trivial, 2 dimension agrees with the Conan-Elkes bound, 8 dimension agrees with the Conan-Elkes bound, and 24 dimension agrees with the Conan-Elkes bound. Notice that the Kepler story, which is d equal to 3, doesn't bound, which actually is telling you the Conan-Elkes bound is the upper bound, but you know, it's not really optimal because in the case that we have certainly solved the 3-dimensional one, it doesn't go all the way up. But this essentially amounts to a numerical proof that in well, in 2, of course, we knew, but that in 8 and 24 dimension, the E8 lattice and the Lich lattice give you the best optimal packing. You see, the spheres do a terrible job at packing. The density decreases exponentially fast. There's also a lower bound, which is exponentially far away, and nobody has the slightest clue of what is the behavior in high dimension. It's an extremely irregular behavior. All sorts of funny things happen at special dimensions, and it's very much a completely unsolved problem to know what is the optimal, if there is a good optimal bound at large dimensions. And so now, hopefully, this will start ringing a bell. This clearly is rather reminiscent of the kind of numerical games that we play with the modular bootstrap. And what Wiazowska did to finish the mathematical part of the story is that she constructed analytically this Konelkis function f of r. And it was a clever answer that used modular forms, and that gave the final proof that 8 and 24 dimensions, in 8 and 24 dimensions, the E8 and Lich lattice are optimal. And so here we're approaching at least one punchline of this talk. How all these threads connect together? Well, I first told you that the modular bootstrap is a way to construct optimal theories of quantum gravity in 3 dimensions. And now I'm actually going to tell you that the modular bootstrap is in turn completely equivalent to the sphere packing problem. And the Konelkis magic function f of r really is the same thing up to trivial change of variables at this linear function that I was mentioning earlier that extracts the information about the optimal value of E1, the highest possible value of E1 that corresponds to the highest gap you can achieve for given central charge. Now, there's a bit of fine print here, more precisely in the story I was telling you earlier about finding the minimalistic theory of quantum gravity. You only want gravity, so you only want Virasoro symmetry, and to get a exam map to the sphere packing problem, you need to also introduce vector bosons that correspond to chiral algebra you want to the C. But that's a minor change. Essentially, the techniques and the results are very similar for the 2 problems. And here is the dictionary. So the number of dimensions with the sphere packing leaves is D, that essentially maps to the central charge up to a factor of 2. And the density of the packing maps to the energy of the lightest state above the vacuum. Now, amazingly enough, in the same year that Wiazowska had her magic function written explicitly, Dalimil Masac, who was at the time a graduate student at Perimeter, had constructed analytically the linear function that solved, well, not quite the modular bootstrap problem, but closely related problem in one-dimensional conformal field theory, which turns out to be equivalent to the modular bootstrap. We had found very concrete, explicit, optimal function that demonstrate, that give you the highest possible gap. And it turns out that the 2 kind of functions are completely mappable into one another. So there is an alternative history that one could imagine. If we had known about this problem in the physics community, physics could actually have solved the sphere packing problem at the same time or before Wiazowska, because we really had, Dalimil had exactly the same techniques and tools. Okay, so this story here is slightly different. I just want to give you advertise. So the bulk of the talk really has been about 3-dimensional quantum gravity. What is the simplest theory of 3-dimensional quantum gravity? And I told you that there is a surprising map to the sphere packing problem, where an intermediate step is the modular bootstrap. But of course, another thing that you can do is to put constraints on correlation function of local operators. And if you do that, then you can, in the case of anti-de Sitter space, you can use the well-known constraints on correlation functions of local operators to learn something about quantum gravity. moreover, ultimately, what you really want to do is to study the less toyish version of the problem, which lives in flat space, where by taking the radius of ADS to infinity, you just reduce yourself to studying the scattering of gravitons, the S matrix of gravitons. And so one can really do both with modern techniques. We can either study the constraints at the level of conformal field theory for 4-point function that corresponds to bootstrapping quantum gravity in ADS, or we can actually directly apply bootstrap methods to the scattering of gravitons. And there is a map between the two, which essentially corresponds to taking this large radius limit. So philosophically, they are very similar. The left corner is a bit more rigorous because the axioms of conformal field theory are uncontroversial, whereas the axiom for the S matrix are a little bit more tentative. We can impose certain physically motivated conditions on the S matrix, but truth be told, nobody never completely understood, despite this very long history that goes back to the 50s, what is it that we should impose about the various analyticity property of the S matrix. And that, of course, gets even more hairy if you
I have a question.
Gravity.
Regarding this bulk computation of the 4-point amplitude, do you consider
Yes.
Witten diagrams? Do you consider the leading order Witten diagrams because of the low value of the G Newton, or do you consider all possible?
No, there's no such thing. So we're not assuming anything, right? So again, I'm not showing any equation, but the idea is that you literally just want to write down the axioms of a 4-point correlator. There's no Witten diagrams anywhere.
No, in the bulk
diagrams anywhere. There's just the abstractly defined correlator, and there's unitarity, there's crossing, and then the physical setup here is that you want a large central charge. And then, as it turns out, if you really want to approximate this with Einstein gravity, you also want the gap, this E1 gap, you also want to take it as large as possible. So under this assumption that you have a large central charge and a large gap, on very general grounds, one can prove that the bulk theory will be described by Einstein gravity plus small corrections. And there's, again, no concrete Feynman or Witten diagram is ever written down. It's an entirely abstract thing that just uses the axioms of conformal field theory. Now, the game is then to constrain what kind of possible higher derivative corrections you can put into the bulk theory, both in anti-de Sitter space and in flat space. In anti-de Sitter space, we can do this in the language of conformal field theory. In flat space, we have to make some, I think, very well motivated, but not fully rigorous assumptions about the S matrix. And then those go down the name of elasticity, crossing, suitable boundedness in the region limit, etc. And so, just to, I'm probably out of time.
So on that, please, I mean, Leonardo, please, if you can get towards the end, because we're running a bit low.
Long. I'm just gonna flash a couple of slides and conclude.
Thank
so
you.
to give you a sample of the things that can be done using this S matrix bootstrap here is again an exclusion plot on higher derivative couplings in a scalar theory coupled to gravity for simplicity. And this again has to be interpreted in the spirit of carving out. So the theory that is consistent in the theory to the right of these curves. And so you see in the space of these higher derivative couplings, you have exclusions plots that are rigorously obtained by under these assumptions. And what you find, for example, is that in the case of dynamical gravity, this coupling G2, which is the lowest allowed higher derivative correction to a scalar, is allowed to be a little bit negative. The intuition is that gravitational time delay compensates for the gravitational time advance that comes from G2. And let me skip supergravity. And this is a very nice plot that came from a recent paper by Caroniot, Lee, Parra, Martinez, and Simos Duffing, where they play a very similar game, but now in something extremely realistic, which is 4-dimensional Ising gravity plus derivative corrections. And they're able to put, again, rigorous constraints on the higher derivative couplings, something like Riemann cube Riemann to the fourth corrections to Einstein gravity, assuming extreme little, again, general elasticity properties of the S matrix, and then we should interpret now the gap to the next state as the gap to the next higher spin state. If people ask, I can tell you more later. And so let me conclude. So I gave you a bit of a composite talk that had many threads, but hopefully the connection has become clear at the end. Essentially, I told you about three things: the bootstrap, which I illustrated most in the context of the modular bootstrap, black hole thermodynamics, and the question of what is the simplest theory of three-dimensional gravity, and the sphere packing problem. And it turns out that in a certain context, they are closely related. We haven't solved this question about what is the simplest theory of three-dimensional quantum gravity, but we have learned something important, that question is intimately connected to the sphere packing problem in a very high number of dimensions. So that's a very intriguing connection because it relates a deep question in physics to a deep question in mathematics. The interplay between the two subjects led to results in both directions. For example, even purely from the mathematical perspective, now we have an improved upper bound for the asymptotic density. And then I just told you a little bit about the connections, a very specific linear programming bound that relates these two subjects, but are there more general constraints? Conformative theories and sphere packings are much richer problems, and one could ask whether there's more general relation between the two. And then finally, towards the end of the talk, I told you at the beginning of this program about using constraints on 4-point functions, both in anti-zeta space and in flat space, to constrain high derivative corrections to quantum gravity. And I'll end here.
Thank you very much to Leonardo for this really fascinating talk. It was full of little corners that all came down at the end. And other questions? We already had something during the talk, but please.
Yeah, I have a question regarding that modular bootstrap equation, Z beta equals Z of 1 by beta. So if this equation holds for all possible beta, that means that you have an infinite set of equations for an infinite set of energy levels, right?
Correct.
So that would essentially tell you that the energy levels are fixed.
No, that's a very elementary logical mistake. It would tell you that you have infinite many constraints, but it certainly doesn't solve. I mean, no. I mean, the two infinities that, infinity minus infinity can be anything, right? It can be 0, it can be 1, it can be infinity.
No, so are you saying that the number of equations are different from the number
Just
of
because something is infinite, something else is infinite, doesn't mean that the same infinite, right? I mean,
no, that's
it
true.
turns out, of course, there are many solutions of this equation. Any two-dimensional conformal field theory, and we know many of those, will satisfy.
Yeah,
the question is very constraining, but it doesn't mean it completely determines the energy level.
Doesn't it over constrain the possible energy levels because you have no more equations than you have energy levels?
Both are infinite. Both are infinite. It's a matter of quantifying how infinite they are.
Continuous infinity, beta is a continuous infinity, and the energy levels are a finite set.
No, the energy level, first of all, are an infinite set, and each of them can take a continuous value. So the energy level are real number to the infinity, and beta is real numbers, right?
The number of energy levels is a finite set, right?
No, the number of energy is an infinite set because the energy can be arbitrarily high.
No, yeah, they're an infinite set, but they're countably infinite, countably infinite.
But each energy can take an arbitrary value. Think about it.
Maybe we can move on to something else.
If there are other questions. Let me convince you. First of all, two-dimensional theory exists. So we know that there are solutions to this equation. That's uncontroversial. And there are many of them. So there are many solutions to this equation. It's a powerful equation, but it surely doesn't constrain the theory completely.
That would be good. No, it'd be good if you could solve any 2D conformal field theory with just one equation. I mean,
Yes.
other questions? Okay, so I do actually have a question about. So one way of asking the question is 9.08 an approximation of 12, or also said
No,
what happens to BTZ?
So
Yeah.
what happens, of course, is that we are imposing a powerful equation, which is the modular invariance, but surely there's much more structure to conformal field theory.
Mm-hmm.
And so the most optimistic scenario is that, of course, there are many other bootstrap constraints you could impose that are necessary to completely make sure the theory is consistent. And by the time you're done imposing all of those, this bound will become optimal. This modular bootstrap on its own does not seem capable of pushing the energy all they want to see.
Oh, wait, maybe then I'm misunderstanding.
So I'm slightly simplifying things. So what this bound, where this bound come, what these bounds actually come from this equation I wrote down to make the equation as simple as possible is the one where I ignore the angular momentum. So this is the spinless modular bootstrap. If you include angular momentum, you could hope to do much better, but in practice, numerically, it appears not to be so. So there is a small hope, which I think is probably not justified, that if you do the modular bootstrap really, well, this has already been tried, but maybe one should try harder by fully incorporating angular momentum, then the bound could become optimal. I doubt it because the numerical evidence is not there.
Mm-hmm. Mm-hmm.
However, the torus vacuum partition function, of course, is just one geometry, right? You could now consider 4-point correlators. You could put torus 1-point function to, the idea is that, of course, we are just looking at an extremely small set of constraints over the infinite many set of constraints, and in the fullness of time, it would be very nice to prove indeed that the bound is optimal, but this particular constraint alone doesn't seem to do it.
But just one thing, maybe I'm misunderstanding, but how am I to read that constraint? So it does. Because the BTZ black hole, if I understand, is below that energy, right?
The BTZ black hole is C over 12.
Right.
Yes, which is below.
Which is smaller than that.
Right. And so that means that, right. That means that we haven't milked the full constraints optimistically. Of course, it could be that.
So that constraint is to, yeah, but I thought that this was excluding everything that was below.
No. Again, it's an upper bound on the smallest E1.
Okay.
So this would be telling you that you can push the bound all the way up to C over 9, but we don't think that that's plausible because we know where we should have microsecond kicking in at C over 12. So that means that this bound has room for improvement.
Okay, perfectly clear. Other questions?
Yes, hello. Can you hear me?
Yes.
Yes. Okay. So I hope this question isn't too at a low level, but you explained how the bootstrap method can allow to create exclusion plots in parameter space, and these plots can have particular geometries. So I'm thinking of things such as kinks, and well, we know that kinks have been they've been seen for the Ising model. But even more recently, I believe you have in a recent paper, you showed that also for pion scattering, there are kinks. And you speculated, you guessed that in this kink, large N may fall on this kink. And I wanted to ask more generally, why the position of the kinks in primary space have particular meanings? And
that's
then
an excellent question. That's an excellent question. So, two things. First of all, the boundary of even if you don't have a kink, if you're sitting at the boundary, which is, not quite excluded, but on the verge of being excluded, it means that you have a particularly sparse spectrum. You're sort of on the verge of ruling something out, which means that you have as few states as possible. And when you have a kink, if it's a true kink and not a numerical artifact, it means that you have two such sparse spectrum that intersect. And so the number of states is reduced even further. So this has been demonstrated very nicely in the case of the famous kink for the three-dimensional Ising model. You look at the spectrum of one curve, you look at the spectrum of the other curve, and at the intersection, essentially, some states get lost. And so, I mean, there's no theorem, but there's just a hunch that theories that leave a kink are particularly minimalistic. They're particularly sparse. And so perhaps they have some enhanced physical value. And that's what happens in many examples of the conformal bootstrap. Okay,
and that's why, let's say that's the reason behind also your guess.
Well, our recent guess, it's still very preliminary. But yes, that's a very general expectation, yes.
Okay, thanks.
Sure.
Do we have other questions or comments?
Can I just press a bit further on what I was asking?
Yes.
So suppose you have 4 equations and you have 3 variables. Okay. Now it doesn't matter whether those 3 variables can take any sort of value. They can take arbitrary values. Doesn't matter. But if you have 4 equations and you have 3 variables, that would over-constrain the system, right?
But here we have infinite many variables, infinite many equations.
No,
you're not going to win this battle because I can show to you infinite many solutions to this equation. I promise there are infinite many solutions to this equation.
No, there might be, but what is the fallacy in this logic that if you have?
I cannot. If I were to find fallacies in all the wrong reasonings, I would be doing nothing else. Sorry.
Well, the fallacy is that infinity minus infinity can be infinity. This is the fallacy.
That's not the fallacy. That's not the fallacy.
No, that is a fallacy because you have a continuous variable, you do Fourier transform, you have literally a countable infinity of equations, and then you can try to set a countable infinity of modes, and then you can get infinity solution, or you can get all the minimal models out of that, for example, and that's it.
You have an uncountable infinity of equations, and you
have a countable infinity of equations. It's a Fourier transform. It's exactly what he has. It's what Leonardo has written in his slides. Do we have other questions?
There is a continuous variable.
Are there any other questions or comments? Okay, if not, I'm very happy to thank again Leonardo.
Thank you very much. It was fun.
Okay, we still have one. We still have one. Go for it.
Yeah, well, it's a slightly technical question about the sphere packing paper that I had written earlier. You also pertaining to what you presented here. So you constructed a map between gamma 2 and the crossing plane. And it is shown that for saturation at C equals 12, for example, you get the modular function of BSL2Z. But my question is, say you consider some other congruent subgroups, or let's say we come from the moonshine. So let's say we consider some other conjugacy class of the monster group, and we find some congruent subgroup that corresponds to it. And if you're able to find a map to the crossing plane, then will that correspond to some CFT, some minimal model, or some irrational CFT, or is there anything interesting going on there?
I'm not completely following what you're saying, but the map, I think if I answer your question, the map that you're alluding to is just the very universal map that allows you to is this pillow map that allows you to map the essentially the torus partition function to a certain 4-point function. That's very universal. It's just kinematics. It doesn't appeal to any details of the underlying theory.
No, I meant the map. Well, I think it's the same, but when you map the fundamental domain of gamma 2 to the crossing plane for the specific case of gamma 2, right? That's a specific subgroup. But let's say
it is a group, but it's just dictated by the geometry of the problem. That you want to reproduce the torus partition function. It doesn't contain dynamical input. It's just literally the kinematics of the problem that forces on that particular congruence group.
I see. Right, which makes sense that you write things in terms of the torus characters later. Okay.
Yeah.
But if you come from the, let's say we find, we take some of the arbitrary congruent subgroup, and that will correspond to some other geometry, right? And we can, in principle, be able to write the partition function in terms of.
Maybe there's some other orbifold of the torus or something that could correspond to other congruent. I haven't thought about it. Yes.
All right. Okay. Thank you.
Okay. So thank you again, Leonardo. It was a lot of fun.
Thank you very much.
Thank you.
Take care. Bye.
Thank you very much.
Thank you.